to video the exact laboratory. Based on the great feedback we got in February as part of the conference, we decided that we'd do a little bit more of a recording around laboratory in order to give you a blend of media this time to explain our topic of printheads, how you choose them and how you use them. So we'll be looking again at the Jet Expert, it's on the other side of the room here, and we'll be testing with a Ricoh head, with a smaller drop size, with more high frequency capability, and looking at the waveform as a function of frequency. And then, using a meteor rig, which is on this side, as before, we're going to look, instead of a smaller drop size, we're going to look at bigger drops, and we're going to look at printing them at a larger gap and the considerations there. So effectively exploring the two ends of the inkjet head spectrum and the two kind of polar opposites or applications. One which is predominance on speed and the other which is predominance on getting material across a gap in order to fulfill a specific application requirement. We'll be doing practical demonstrations, like I said, and we'll be showing, hopefully, some samples at the end of it from each of the inks that we use. Like before, we'll be highlighting where we're using other FuturePrint partner technology, as well as that from other vendors, in order to give you an idea of the value presented by the combination and collaboration of suppliers within the inkjet ecosystem, something that we very much believe in, and is one of the key motivations behind events like TechFest. So, without further ado, and without the computer interrupting, let's get on and have a look at some of the detail.
So before we get into the practical demonstrations, just wanted to introduce the reasoning and rationale for doing this as a lab demo. An image expert recently posted a list that is quite comprehensive in terms of discussing what's available in the market. Selecting printheads isn't just about a list of specs, deciding what DPI. Although for individual applications, it's really important to understand how much deposition of a material you need in order to reach the desired result. And that depends on both the drop size, the DPI to some extent in both directions, and of course, it depends on the chemistry you want to put through and the head selection that results from that chemistry. But what we're going to do is not work from a list, but demonstrate two heads at different ends of a spectrum in order to put into context what the different properties of the printheads mean.
It's going to take some time to introduce the Jet Expert system. And actually, unlike the last video, we're doing this with everything currently not running, just so there's less background noise. There still is a bit of an echo, it's a big room, but hopefully you can hear me better. So the Jet Expert system combines a conveyor with a drop watcher. And the idea is that you quickly can change between the two just by sliding the head assembly across. In our system, it's quite populated, because we use it for a wide number of different printheads. That means it's set up for not just GIS electronics, but also meter electronics and all the cabling to make that possible at once. In addition, although currently we're running the GIS ink system here, hidden a little bit under the insulation, we also have the cabling and the tubing to run the MagnaJet ink system, should that be either preferred by the customers or preferred in terms of the spec of the head. Okay, so let's have a detailed look at the head assembly. Starting with the printhead, at the bottom here, mounted is the Ricoh MH5421F, colloquially the Gen 5F head. There's two colours, nozzle recirculating, and it's connected each row, which could in theory be a different colour to run 300 dpi two colours, is both connected to the GIS ink system with the same black ink, but one row goes to one outlet and the other row goes to the other outlet. So it just simplifies getting the tubing lengths matched and getting the pressures matched into this printhead. You can see there's a fair amount of insulation around the tubing. Even though the printhead has a heater, it's good practice to try and maintain as much insulation and much thermal transfer from the main system heater through to the head. I've actually removed the insulation that in the intro a moment ago was attached, just so you can see the reservoir to the GIS ink system. And above that are the pneumatic tanks. And behind here are catch pots which stop any ink overflow from the tanks damaging the pneumatic tank solenoids. Go one step further back, you should be able to see that behind here is the GIS ink manager board, and that's doing the control of the solenoid and pumps in order to keep the pressures in these tanks at the set points, thus forcing circulation through the head and back. The head is driven by here the meter electronics, so we have the PCC, printer controller card, and we have the HDC, the head driver card. Add-on here is a fan that cools the heatsink for the HDC for higher frequency driving. And really, that's basically what we need to drive the printhead. Now we are looking at the GIS GUI for the ink system. You can hear in the background, I hope, the chirping of the pumps and the vents that are controlling the pressure on the IMB system as showed just a few moments ago. In the software, what you can see on the left-hand side is a status, and it's currently heating at a set point for the heater, which is a preheat. And then on the right-hand side, we have the inlet and outlet tank pressures, the inlet being positive and the outlet being negative for the flow-through Frigo printhead. As we move along, on this screen we have the Meteor software showing a simple 3-pulse waveform that we're going to start with, and you can see, perhaps, although not in detail, there's an orange light there, and that means that the head isn't quite hot enough yet. At the moment I haven't turned on the head heater, and so it's just the heater from the preheat that's getting through to the head. And waiting to see that that gets to a value that's high enough that the head heater is only doing the last little bit. What I'll do now is I'll enable the head heater. And then we have the Jet Expert screen. Because it's not quite yet to temperature, we haven't yet started firing. What you can see at the bottom, just about, is the frequency generator, which is part of the frequency sweep or latency add-on, and next to it is the remote control, which is part of the motion upgrade. Those two accessories help us do a wider range of experiments. And then we now have the head of the Jet Expert. Then that's actually partly obscured by this fan assembly here, and this is just protecting the Jet Expert box from any ink mist that may be coming from the capture, because if we pull it into the Jet Expert box, then it contaminates the electronics there. So this very simple arrangement is just ensuring that doesn't happen. And then we have the head in the Jet Expert position. What we're going to do next, we're going to zoom in on that and have a little look at what we're doing at the Jet Expert and the view of the head alternately.
So here we're jetting a single row as visible on the Jet Expert, changing between grey levels. We pan over to look at the print head, and jetting only one row, it's quite difficult to discern the line of jets, but you can see a little bit of a mist as the air flow misdirects the jets. So what we'll look at next is what happens when you jet all the nozzles. We're now looking at the head jetting at 2 kHz, cycling through the grey levels of 1, 2 and 3. You can see that the drops get caught in the airflow and cause some deviation. The drops flow slightly better as the drop size increases, but the biggest effect comes from frequency. Now switching to 10 kHz, it's just 2000 drops. It takes a fifth of a second to print. You can see a cloud of dust created instantly. as you continue to increase frequency, the ability to see the drops gets even harder. They disappear in just 0.1 second. So what we'll do is we'll demonstrate some static images in a moment. But you can see that they project much faster, and that's because of the entrained airflow caused by the ejection itself. Let's have a look at that as static images so we can actually see the detail. We can see the images now arrayed side by side, and it's apparent how the jets at higher frequency form these neater streams. And that's in fact quite similar to continuous inkjet, where a continuous stream of drops can be made to cross a bigger gap because of a higher velocity. In this case, the velocity is actually matched, so it's the entrained air that's allowing the drops to travel further without the production of mist, and it's in the presence of turbulence that mist begins to form. And this is important for different applications, and particularly ones which go very fast, and the air entrained in the substrate can have an influence. So we have a waveform now offering 3 drop sizes. What we're going to do next is print.
Once we've got the waveform in place, the next step, using a print station, is unsurprisingly to deposit some ink onto a substrate, leftwards, print test. So although we're just going to make a quick demo like we did before, what we're actually printing is a slightly more detailed image, which will enable us to then look on the microscope and compare the print as a function of speed and as a function of the waveforms that we looked at. Now, it's quite difficult to avoid making some noise at this point, so I'm going to turn the belt on and then it will become a bit more difficult to hear me. We've got the UV LED, and so for that reason I will change my glasses like last time, just to avoid any issues relating to the UV light. And then it's a question of taking a substrate. In this case it's photo paper, so we can do the subsequent analysis in some detail. You can see exactly where the drops land, and you can see their diameter as a function of the different grey lines. We push that under the head. Once that's in place, we just have to supply the data to the printhead. And we do that by instructing the Meteor software. There we go. I could have done it, here's what I did earlier. But actually what we're going to do is we're going to run at 2 different print speeds and show you the different performance on the belt. And so I'm going to be turning around to press print another time. So we have UV LED belt on, it automatically stops, and then UV LED off. Simple. So this is our first print at 20 meters a minute, pinned by the LED. Now, same thing again, but we're just going to increase the speed of the belt. And look at the effect it has on the drop placement and image quality by microscopy. So we've doubled the speed from 20 to 40 meters per minute. Start the data again. Hard to see the computer screen and read on, particularly since I'm not wearing my specs. And then again, LED, belt, stop. So you saw that was much faster. The print just about on the paper this time. And then, as a final print, we'll do one at 60 meters a minute. This time it might move a little bit past the stop sensor because of the speed. LED, print, LED off. Here's our print. at 16 metres away. Let's have a look at those by microscopy. So we have our 3 samples printed at 3 different speeds arrayed here. So let's have a look at what the image content contains. So designed for TechFest especially, and acknowledging some of the partners involved. See the inset photo. The test pattern includes a variety of text, both reverse text and actual text at different font sizes, and in the different grey levels 1, 2 and 3, an increase in a ordered diver of coverage. Let's have a look on the microscope. So this now is just a very low cost USB microscope. You can see immediately that on this photo paper the UV ink stands out and is quite reflective against the background. So you can see the LEDs of the ring light picking out all the reflections of the curved surface of the print. Let's go down to where the isolated dots are. So this is the grey level 1 dot. That is in focus as we're getting, hopefully you can see that. And then we can move across to the grey level 2 and the grey level 3. So you can see the effect of the waveform on the droplet diameter. If we go back to this section, what we have is text. It is just 10 pixels tall, so that would make it about 0.4 millimeters. And each line in the text is approximately 1 pixel across. So what we can do is we can compare that text as a fine feature between the 3 speeds.
And here are the images arrayed for convenience. From left to right, we have the increasing speed that we've just demonstrated. And then from top to bottom, we have the different droplet speeds created by different waveform optimizations, where each of the 1, 2 and 3 grey levels have been matched for the droplet speed. And typical with a UV ink, the satellites increase with the droplet velocity. And so in the bottom row, you begin to see the effect of that. And because the head's being driven harder, you also see the effect in the deterioration of the level 3 drop. The head is effectively being driven too hard and nozzle failure is resulting. But it can be seen that for the 6 meters per second waveform, OK print quality is obtained up to 60 meters a minute. At 7 meters per second waveform, arguably the print quality and drop placement is slightly better at the higher speed, but satellites start to form. At the even higher droplet speed, those trailing satellites become very noticeable and start to affect the text. But we should keep in mind this text is very, very small, but to the naked eye it's practically unreadable, so those satellite issues are relatively minor until they cause mist. And with that analysis, we complete our demonstration on the Image Expert. We'll now move to the Meteor rig.
Okay, so I'm aware that not everyone may have watched my previous video in the conference programme in February. So what I'm going to do is very briefly introduce the rig, and then I'm going to highlight the changes since my last one, which will help those people who did watch. So the equipment here is underpinned by the drop watching capabilities arising from the Meteor drop watcher. So therefore all the driving hardware mounted on each of the 3 head positions is hardware that goes with the drop watcher, and so each head can be driven independently, one at a time. The layout of the heads is very similar to last time, so we've got a Seiko RC1536 here, we've got a ZAR 1003 in the middle, and on the end we've got the Matic SG 1024 SA. And actually, Seiko, ZAR and Fuji, or Fujifilm partners, of course. So the main difference to last time actually is not that we've got heads on it, because that's what we showed, but that we've added a modular component for different types of printing experiments. So we demonstrated previously a print by running with a large bottle on the conveyor, where there's sufficient space underneath the print head in order to put a large bottle. Now what we've added is a linear stage, which is currently located underneath the RC head, where we'll demonstrate it, and that linear stage enables us to test at different speeds with much more precision and with acceleration that isn't quite so possible with conveyor. So let's have a closer look. So this is our latest addition, the IGUS print stage, the length of which is chosen so that we can move it underneath each individual printhead position and still service or do drop watching or even print with the conveyor on the other head positions. So it's designed to slide along, just like the conveyor itself. Print position can be changed very easily. The other main feature of this stage is being a bit more precise than the conveyor. The conveyor is only a very simple one and can suffer from a little bit of weave, which in the most precise printing you can see. So this stage lets us do slightly more precise experiments. Also, the acceleration and the speed is much better than the conveyor, which we can demonstrate by simply sending it back and forth. So that's an introduction to our latest upgrade. We're going to be looking at a different regime of drop sizes now, starting at a similar drop size to Rico, but ending at a much higher volume. Then we're going to use that higher volume to demonstrate printing at a larger gap. But first, let's have a look at the drop watcher and see what these drops look like on the Meteor system, which is here. You can just about see the printhead, you can see the blue light of the LED, and on the screen you can see the drops. The ink is being supplied down this tube for this pressure module, which is part of the Tsar Hydra, which we talked about in our conference talk in February. But just to review that, if we look here, we can see the pressure control chart of the Hydra, and it's showing the pump speeds versus the set point pressures. And in this experiment, we're using a differential between in and out on the printhead of 110 millibar. Back to the jetting. On the screen, we currently have drops for the first grey level, and we're using 5 grey levels. Each grey level adds an additional 2 pulses, up to a maximum of 10 pulses. So on this RC1536M printhead, we have a maximum drop volume of over 100 picolitres, or approximately 100 picolitres. And we can see that by zooming in, so I will just highlight the region of interest so you can see the drops. And what the software is constantly doing is looking for the drops, locating them, drawing circles around them, and then in this plot here, showing us the speed, the diameters and the volume. So at the moment we're looking at about 2 millimeters from the faceplate, and we're going 7 meters per second. And we can then cycle through the grey levels and see the change.
So that's actually much easier to see if we separate out the screen elements of the control of the grey level, the drop view, including the features highlighting the drops, where measurements are derived, and the measurement window itself on the right there. So now what we're going to do is cycle through the grey levels, which you'll see on the left, see the different changes in drop size, and then be able to read the characteristics as they're calculated on the fly. So let's do that. So we start with GL1 and then 2 and then 3, and each time you can see the drop size increase. So it's averaging, so towards the end of the measurement on each drop size you'll be able to read the correct range. And at the end there we go over 100 picolitres. With the defined drop sizes that we've just demonstrated, we're now going to make some print trials onto paper plates and paper bowls, a simple substrate, to demonstrate with the water-based ink we've got installed the benefit of large drop sizes, but without the curing limitation of using a UV ink like we did in our last demonstration.
So we're looking at the print stage here, and what we have is a spacer in order to allow for the difference between the bowl and the plate. So let's start with the plate. So we'll send the stage back and forth and you should be able to see it printed. Let's have a look at that. So it's possible to see that the grey level 1 has become quite vague at the bottom of the plate compared to the top. But most of the other grey levels are resolving pretty well, and we can still see 1mm text. Now let's move to the bowl. This time you can see that we've actually completely lost the grey level 1 at the bottom. The grey level 2 is becoming quite vague, and actually even the grey level 3 and 4 show some variation, with only really the 5, as used in the logos, actually showing some ability to resolve pattern as intended. You can see the amount of ink here is causing beading on this waxed paper. So when you put down so much ink as 100 picolitres, you need something for it to be handled with either absorption or curing or drying, and in this case we haven't dried. But it gives you a good indication of how flexible large drop size printheads can be at larger distances onto different shapes. Now if we move the printhead stage back, what we'll see is just how big that gap is. So we just recorded the gap as 35mm, and one of the challenges when printing at that sort of distance is the influence of airflow, and particularly when you print a shape like a bowl, because the air can get trapped as a circulating current within the contours of the bowl. And the best way to demonstrate how that can happen is to increase the speed to increase the eddy currents formed by the motion of the bowl relative to the head. Last time we printed quite slowly. We printed at just 100mm a second. So that really only drives the head about 1.5 kilohertz. So now we're going to increase that to just over 200mm a second. So the head's firing 3 kilohertz, which is the same setting as we viewed on the drop watcher. So if we look at this bowl, we can see the RC1536 lettering actually probably looks a little bit better than it did on the last one. And that's because potentially the entrained air from the firing of the drops at higher frequency is helping them reach the surface a little bit better. But let's just go a little bit further and have a look. So for 6 kilohertz, so 420mm per second, we begin to see the loss of a resolution by printing at speed. So it demonstrates that printing at distance is perfectly possible, but to expect to do it at the high production speeds you get on a roll-to-roll system is unrealistic. And as one final example, we have this triangular section, which is actually paper wrapped around an extruded plastic profile. So here we're just demonstrating a different type of shapes. And this time, the image is compensated for the angle of the slope, so that the pattern reads, when you look at it, correctly instead of stretched out. Let's see that. So with those videos looking at the printing itself, that's our practical demonstration of inkjet printing at distance completed. And what we'll do is just cut to a couple of analyses of what it looks like, both on the shapes and on the triangular section, to give you a feel for what's possible.
Here are the print samples arrayed as photographs taken with a phone camera, and you can see the differences arising in the bowls quite clearly as a function of print speed, with actually the medium speed or the slightly higher frequency providing a best print quality because of those airflow effects we spoke about, but a complete deterioration at high speed. In comparison, the plate's much more consistent because of a smaller gap, but the higher speed does begin to lose quality. The triangular profile looks quite good overall for the type of area pattern we applied, but you do tend to see a loss in the resolution of the text of the logo when you get above 20mm away from the printhead. And this just goes to show that printing at distance is always going to be a pattern dependent effect as to how successful it can be, and it will depend on how you can hide the deviations that stop things like text from looking perfect. And in some graphics applications, that's perfectly possible.
On either side of a room, we've demonstrated how it's possible to use printheads and test with them in order to arrive at the right printhead for the right application. Whether it be high-speed roll-to-roll for labels or packaging, or whether it will be something as simple as printing picnic plates, but more realistically, extruded profiles and sections, a much more industrial need for decoration. And so what we'll just do now is wind up for today. I'd like to thank you for your attention throughout this video session. I hope for those that caught my last one in February that this one has been just as good, if not better, and I would very much appreciate any feedback anyone has, and I'll be available during the TechFest event, so please catch up with me and also see my session, hosted session recording, talking about the selection of inkjet components and their integration. Thank you, and goodbye for now from DoD Exacts Laboratory.